interesting keynote and exciting keynote on the new systems thinking to drive high performance computing and machine learning. We have Mr. Jay Hiremath, Corporate Vice President, Systems Design Engineering at AMD, who will be addressing this keynote. He leads the software group. His team is responsible for AMD's advanced toolchain development and productization, including compilers, libraries, profilers, and machine learning inference solutions, and also business critical debug tools, system management tools, and platform software solutions. Mr. J did his bachelor's in electronics and communication engineering from Karnataka's PDA College of Engineering. Then he spent about 3 years as an R&D engineer at Bharat Electronics before he was heading to Tennessee Technology University in US to pursue his master's degree in electrical engineering. He worked as research assistant and did his graduate thesis in field of neural networks 20 years before machine learning and artificial intelligence would come to dominate the tech sector's vocabulary. He then spent the next 12 years in Silicon Valley with microprocessor maker NextGen, which was subsequently acquired by AMD. The highlights of his 25 plus years of journey at the company is closely linked to AMD's growth. He began his journey in California and moved to Bangalore in 2005 to help in setting up the design center in India. He had continuously demonstrated the ability to successfully lead and execute his multiple concurrent complex programs. AMD's potential in things such as machine learning, high performance computing power offered by AMD's IPs both on the CPU and GPU side fueled a phenomenal growth in the company. Being a part of many such critical game-changing product contributions, including the stellar success of Ryzen and EPYC, today is what he defines as the most exciting part of his career. So nice to have you, Mr. J.
Thank you, Satish. I'm audible, Satish?
Yeah, you're audible.
Thank you. Let me share the screen to get started. So Satish, again, thank you for the kind introduction. Truly appreciate it. And also, before I get started, I want to take this opportunity to thank IESA team for extending this invitation to me and offering this platform to share my thoughts on HPC and machine learning, AI, machine learning, and very relevant topic, if you ask me, in the day and age that we are in today. It was not so, as Satish was alluding to, when I graduated a quarter of a century ago, more than that actually. It was not so. It was a little ahead of its time. The things that we studied, they're coming to becoming more relevant now, have become relevant, and if anything, my thesis was a little ahead of its time, I guess, right? So, but I'm very glad to hear, and I'm very glad to be living in this era of supercomputing, machine learning, high performance computing. Any which way, some of these things are used interchangeably, but very, very exciting days, if you will. Now, the reason I say it's a very relevant topic is, if I had to use one word, then that word would be data. In fact, 3 words actually: explosion of data. Because if I throw some data points there, for example, we are surrounded by connected devices all around us, right? So about 10 years ago, a little more than that, maybe, IoT was the in thing. There's the latest buzzword, and all of us in the tech industry, and maybe even beyond tech industry, wanted to get involved in everything IoT. Check that box now, because we all are involved in one way or the other. We are involved to the point that today, as we speak, give or take, there are about 8 billion connected devices worldwide. It doesn't stop there. It is expected to grow 10x almost to 75 billion by the year 2025. Now, when these many devices are interconnected, the data are being generated, because every which direction you look at, there is data being generated. It could be as simple a transaction as a point of sale transaction in a grocery store. There is data generated. Or the data center, of course, obviously will churn a lot of data. And even as simple function as facilities management will be generating data. And so this data generated by itself may not mean much. So that's why there is traffic that data needs to move from one place to the other. It needs to be analyzed. And so that's where the traffic comes in. And according to Ericsson, there was a projection made that between the year 2018 and 2024, this traffic is expected to increase 5x, and we're in the midst of that period. And much of it is fueled by the 5G infrastructure. And there's one other thing that most of us do, I would say without exception, in this virtual room, even outside the virtual room, which is searches. Right, so 6 billion searches a day and growing at 10 to 15% per year. And if you annualize it, roughly about 24 trillion with a T searches a year. Right, everything here that I'm referring to is generating the data. And so people are acting on it. For example, Microsoft, they released the deep learning optimized library for distributed training, because it facilitates easy, efficient, and effective training of distributed systems to the tune of 100 billion models that can be trained. So people are working on it, and the deep speed library that I'm referring to is the open source library that is being used, and it's being put to use already. The Turing natural language generation has leveraged the deep speed library, for example. So the point is, there is data all around us. And that is why high performance compute and machine learning and AI are very, very relevant topics. That's, what I'm going to talk about is a system view of how to deal with this. Just look at the workloads, right? In the future, what are these workloads asking us? What are they asking for? So whether it's a cloud or a supercomputing setup, or on the other end, client solutions, gaming, AI systems, each and every one of these, and not to forget the communication infrastructure that we talked about earlier, right? So we are looking at churning this data, analyzing data, simulating them to make decisions based off of this data. Right, so this translates to power, compute power, and all around us, there has been technological and continue to be technological advances, but in spite of that, there is an insatiable hunger for more compute power. And as there's not too long ago that, we used to talk about the client server model, where the client, for the most part, would be a dumb terminal, could be a dumb terminal. It still is there in many use cases there, but more and more, even the client or the devices that are working on the edge are expected to have compute power, edge compute, edge inference, right? So the point is, there is an ask of increased amount of compute power. That's what the workloads are demanding of us. And what are the trends that are driving this, the workloads? If you ask me, when you look at it, there are three things that jump out at us. One is heterogeneous compute, and then the coming together or the confluence of data science and big compute. And the third one, and this is close to my heart, is software enablement. So we'll double click on each of these. So heterogeneous compute or heterogeneity is basically, if I had to simply say it, it's integrating many traditional incompatible technologies. At the simplest level, we are talking about the chip level heterogeneity. There's a CPU, there's a GPU. I've been at AMD for most part of my professional career, so I can easily talk about what heterogeneity it means in the context of AMD, which is relevant to CPUs and GPUs, right? So the simplest example that I can think of. So that's what heterogeneity is. So why is heterogeneity important? Because if you want to design and manufacture huge chips, that will serve a particular purpose, then you need to worry about the cost associated with manufacturing those too. So that's where we can leverage heterogeneity, and which basically is offering us two advantages: product agility and targeted optimization, because each chip in this heterogeneous system is specialized. You can almost look at it as a custom chip for multiple use cases. That's what you can slice it and dice it based on your use case, and that's what the heterogeneity gives us the advantage in. Now, another look at heterogeneity, because where we are today, I mentioned, right? So CPU and GPU at the chip level, we have the heterogeneity today. So the CPU here and the GPUs, constitute the simplest one. They're interconnected using I'll talk about this a little later, the interconnect technology that we have, right? So this is simplest one that I can, refer to today. But where do we see this going? Right? So see it at system level. Much of it is there even today. The heterogeneity permeates to a system level heterogeneous system, and even at the memory level, where you have the DDR memory, various different kinds of memory, working together in a heterogeneous system, DDR and DIMM, and fabric attached memory. That's the memory level heterogeneity that I'm talking about. So that was the first trend, heterogeneity. The second one is the confluence of data science and big compute. Very simply put, all the advances, right? Whether it's data, compute, or the advanced research that's going on in the algorithm area, it's changing the landscape. And if I had to simply put, there is a saying that is attributed to I think, basically it means the whole is better than the sum of the parts. That's what it comes down to. The combined compute and advances in the classical compute, coupled with the advances in statistical learning leading to data sciences, will enable us to cater to far more use cases than these two individually can. Right, so that's the that's the power of the confluence of the coming together of data science and big compute. Yes. So we talk about AI, machine learning, right? So where it is today and where it is heading. So today, we talk about training and inference. For the most part, training is GPU based, and inference is CPU based. It is not to say that you cannot use one for the other. Can CPUs be used for training? Yeah, potentially. I mean, it's technically possible, but does it make sense? No, because the architectures of each of these processors lend themselves to to what I mentioned. GPU, enormous amount of training data can be handled much easier by the GPU, so that's what is there today. GPU based training and CPU-based inference, majority, more than 70, 75, 80% of the inference market today is CPU-based. That's today. Future, we see this machine learning or ML expanding its reach. Then we talk about self-optimization, model distillation, approximate computing, right? Where accuracy may not be the most desired thing. We can make do with some approximate decisions. So those are the areas where machine learning is reaching out to. And of course, inference for low power environment, these we can always can even now relate to those things, right? So the point is, machine learning is evolving as we speak. Now, the third part, which I said is close to my heart, and many of you in the semiconductor industry can relate to this when I said, well, I'm a software guy in a hardware company. Some people may say, well, that's complex enough already. Well, it was, but there is more and more growing realization that software is perhaps the most critical part, because all the compute power without effective software might not mean much, if anything, right? So it's gotten better, but in all seriousness, the challenges in front of software are huge, because as I mentioned, heterogeneity is increasing. We saw this moving from chip level to system level to memory, right? So the software needs to harness all these together to basically cater to the use cases that we have in mind. So that is something that the software has to deal with, the complexity involved or brought about by the increased heterogeneity. And then the programming domains, they also increasing. Memory, storage, the NIC based or the network or interconnect based programming domains, they present new challenges too. All these complexities need to be addressed while keeping an eye on the cost associated with the movement of data, right? So that is what the challenge is in front of software. Now, there are things that can be done in software itself. I mean, this is basically a philosophical thing, right? So whether we can help ourselves, make it a win-win by collaborating, is what it depends on. And we at AMD are big believers and supporters of open standards and hence open ecosystem, because it's a win-win. You collaborate. Yes, you compete with each other, but at the same time, collaborate for the greater good. That's what open source and the open ecosystem brings to the table, right? So open source is a big part of our strategy, right? Open source software in this case, I'll talk a little bit more about this. It basically helps accelerate the innovation. And as I said, for a better world. So what do we do on the open source? I have some examples here, right? So on the machine learning side, you have MLPerf, or the ubiquitous framework, PyTorch, TensorFlow, or excuse me, the Linux, GCC, and then Fortran, C++, OpenMP. All these we are active in, and our graphics stack, we call it ROCm, right? So it's open sourced. And I didn't mention LLVM because I wanted to talk a little bit more about this. We have optimized compiler, right? So optimized compiler for CPUs and GPUs, and those are LLVM based. So if you get into the LLVM repo, there's a good chance that you will see commits from AMD engineers in the recent past, because we are very active. We try to stay top of the trunk, and we try to commit back or changes back to the LLVM community. Of course, there is the associated acceptance cycle that goes through. But the point is, we embraced open source, and we continue to support open source and also open industry standards. Now, while on the topic of open source, I just want to take a moment here to talk about our inference offering. I talked about inference, right? So which is primarily CPU based today. We recently introduced ZenDNN. It's a CPU inference library. We released the version 3. I think it happened late last week or early this week. It's basically an optimized library, and it optimizes the APIs required for the usual use cases, right? So natural language processing models such as BERT or and transformers, or on the image classification side, ResNet 50, for example. And then it also is optimized for recommender systems such as GLRM, wide and deep, right? So it's available for download. I have the link here. The point is, it's not open source yet, but we are working on it, right? It will be open source later, and not far in the distant, I mean, in the immediate future. So that's what is going on. So it's basically, optimized for AMD CPUs. That's and this is an inference solution that we delivered, which will be open source shortly. The binaries are available for free downloads on our developer.amd.com website. Now, that is where those three trends that we talked about: heterogeneity, the coming together of big compute and data science, and then the software enablement. Now, future requires innovation in all dimensions, and I think it goes without saying, and I'm stating the obvious here, but the four that we talk about are, the three we already talked about: silicon, systems, software, and security too. And increasingly, security has become important. We need to have scalable solutions on the security side, starting from IoT and to the cloud and everything in between. Right? It has to be secure transactions. If you don't, if you don't secure transactions and its end-to-end security is not provided, then you are open for breaches, right? So we know all that. We have been enough examples on this. So that's the security part. But others, silicon, we talked about this, right? So yeah, theoretically, you can keep on increasing the compute power, but you also need to keep an eye on the power consumption. And so it has to be efficient compute, and power optimized designs is what we need from the silicon side. And systems, right? So you could have the best in class, very high power, high compute power components, but if there are bottlenecks in connecting the two, then it's no good, because as we all know, the slowest one determines the throughput or the efficiency of a heterogeneous system. So interconnects, memory, and topologies balanced to address the performance bottlenecks is what we need from a system perspective. Software, we talked about this, right? So self-optimizing software, basically bringing everything together. And software is the one that facilitates accelerated computing. And so open source software and more innovations on that side is what is being asked on the HPC side or machine learning side in the future. Excuse me. So that is what the trends talk about. Now, what are we doing within AMD, right? So how do we meet this demand? And for us, the journey started, this is 21, so about 15, 16, 17 years ago, the HPC and the, not so much, it was not a machine learning journey then, but it started off as HPC, right? High performance compute. But the point is, and again, this is a no-brainer, being in the technology industry, everybody can relate to this, relentless focus on technology innovations, right? CPU and GPU innovations, then you design them. That's what is the CPU and GPU design community brings to the table. And then by manufacturing them with leading edge process and packaging technology, and then interconnect the best-in-class interconnect technology, all brought together and facilitated by software, basically facilitating accelerated computing is how we look at it. We'll talk a little bit more about this, right? So very quickly, what we have on the CPU roadmap. So we are currently shipping, the Zen-based architecture. It started in 2017. Zen is the architecture family name. Zen 1 was shipped in 2017 based off of 14 nanometers, and then Zen 2, the second generation Zen architecture, based as chips. The family was called Rome. That was in 2019. And as recently as last month, we shipped the servers based off of Zen 3, the third generation architecture based on of 7 nanometer technology, process technology. Zen 4 is scheduled for next year, and that will be on 5 nanometers. So very similar story on GPU. Of course, on the GPU side, we have two. One is on the gaming side, we call it RDNA, the gaming architecture. And on the CDNA, the GPU compute side is called CDNA. Very similar story. 2019, we had RDNA on the 7 nanometers, currently shipping RDNA 2, on 7 nanometer, and then RDNA 3 is in design. And similar story on the GPU compute side, very analogous to what's happening on the gaming side. So this is the GPU side of the course. Now, packaging, this may or may not be so apparent, right? Because from an AMD perspective, we have been leading the industry in terms of the packaging technology too. Back in 2015, the high bandwidth memory HBM based GPU was we started shipping that, and since then we have shipped many other GPUs based on HBM technology. In 2017, again going back to the Zen CPU, we innovated with the multi-chip module, and the second generation of Zen in 2019 was the chiplet technology.
We have time is running short. How long it will take to complete this, please?
Sorry, what was that?
No, this time is overshooting. How long it will take?
Another 3 minutes.
Yeah, thanks.
Yeah, so this is what is happening on the packaging side. So now in the future, we have, we are working on the X3D packaging, 2.5 and 3D based technology, which will result in bandwidth and density of greater than 10x. So that's what's happening on the packaging side. So this is the one that I was talking about. You need to avoid bottlenecks, and by facilitating the data flow between various heterogeneous components, right? So first generation, we call it Infinity Fabric. First generation was in 2017, basically on the CPU connectivity between CPUs. This is the first generation Infinity Fabric. And the GPUs, CPU to GPU connections was based off of PCIe 3.0. Second generation is basically GPU. You saw the second generation Infinity architecture provided CPUs was first generation, GPU second generation, and third generation is going to be delivered later this year in our supercomputer delivery, which will happen by the end of the year. So that is basically CPU and GPU, completely coherent connectivity. That's what will be offered on the Infinity architecture. So again, all this, if you look at this very quickly, CPUs and GPUs in their own way right now, CPU data locally to CPUs, GPU to GPUs, leading to the CDNA2 architecture, unified data, offering ease of programming and improved performance, and basically a CPU and GPU coherency with the third generation Infinity architecture that I was referring to earlier, right? So that's what it is. Now, supercomputing makes is a relevant topic. It's if you look at this, basically, from 2005 to now, we have been in the supercomputing industry by winning the deployments and delivering AMD technology-based solutions. And we also had the exact scale program funding that started in 2012, going through right now. So later this year, I was referring to the supercomputer that we'll be delivering to Oak Ridge National Labs called Frontier, delivering 1.5 exaflops of supercompute power, basically AMD CPU and GPU delivered through AMD software. And then there is the follow-on to Lawrence Livermore called El Capitan in 2023. Now, HPC funding, so just a quick word on this, because we announced last year, through the epidemic, when it hit us badly, we announced a $15 million funding in terms of AMD technology to help aid the research associated with the pandemic, so that it will facilitate the research activities on that. So many universities across the world have leveraged this. 1 petaflop of compute power is being donated to these research institutes, and this is across the world. But in India too, we are working closely with CSIR, the government wing, for Paradigm. So that is being deployed as we speak. So that's where I wanted to pause.
Yeah, thank you so much, Jay. We have a few questions, but we'll take, in the interest of time, we'll take offline.
Yep.
Yeah. Thanks a lot for your time.
Hey, thank you, Satish.
Yeah, thank you.
Thank you all.